Jai Hind students, welcome to my YouTube channel. Students, ships don't sink because of water around them. Instead, ships sink because of the water that gets in them. So you can apply the same principle in your own life. So basically, don't let what's happening around you and your surroundings get inside you and weigh you down. Again, I repeat students, ships don't sink because of the water around them. Ships sink because of the water that gets in them. So basically what I am asking you to do is that don't ever let what's happening around you get inside you and weigh you down. So basically in simple language, don't get influenced by external conditions. Believe in your abilities. Trust your abilities. Have that confidence. Right, students? So with that, let's begin this session. In the previous two lectures, we have discussed diamagnetism on the basis of electron theory, and then we have discussed paramagnetism on the basis of atomic theory. Now it's turn to discuss ferromagnetism, and we'll discuss ferromagnetism on the basis of domain theory. Basically, students, there is no much difference between paramagnetic substance and ferromagnetic substance, right? In para, each atom possesses unpaired electron, and each atom thus behave as a magnetic or atomic dipole. Same is the case in ferromagnetic substance as well. Every atom of a ferromagnetic material possesses unpaired electron. So as a result of the orbital motion of this unpaired electron around the nucleus, it will constitute time current loop, and thus every atom of a ferromagnetic material will behave as an atomic dipole. So let's start with the theoretical part. So each atom, due to presence of unpaired electron, possess some non-zero finite value of non-zero finite value of magnetic moment. It's same as was the case of paramagnetic substance, right? So every atom of a ferromagnetic substance possesses unpaired electron, and we know that due to the orbital motion of an electron around the nucleus, the atom possesses magnetic moment, and due to the unpaired electron, it won't get cancelled out. So therefore, every atom possesses some net non-zero value of the magnetic moment, right? So therefore, students, every ferromagnetic atom behave as an atomic dipole. It behaves as an atomic dipole. So this is exactly the same point as we have discussed in paramagnetism. So where lies the difference between para and ferro? In ferromagnetic substances, students, the interaction between an unpaired electron of an atom with another unpaired electron of the neighboring atom is very strong. And due to this interaction, which is known as quantum mechanical effect, so due to quantum mechanical effect, which is also known as exchange interaction, which is also known as strong exchange interaction. An electron, an unpaired electron of an atom strongly interacts with the unpaired electron of neighboring atom, right? So due to quantum mechanical effect, which is also known as exchange interaction, an unpaired electron of an atom interacts strongly with unpaired electron of neighboring atoms. So this is the reason, this is the difference between the paramagnetic substances and ferromagnetic substances. In paramagnetic substances, students, the atomic interactions between the atomic dipoles are quite weak. But here, due to the quantum mechanical effect, which is also known as exchange interaction, an unpaired electron of an atom very strongly interacts with the unpaired electron of the neighboring atom. So, due to this strong interaction, these atomic dipoles tends to align themselves in a common direction over small volumes of the specimen. These small volumes of uniform magnetization are known as domains. So it is by this concept of domain that we will be able, or we will rather try to understand ferromagnetism, right? So that is why we are dealing the topic of ferromagnetism on the basis of domain theory. So before we start with the actual topic, we need to aware ourselves with the concept of domains. So due to this quantum mechanical effect, which is known as exchange interaction, as I have told you, an unpaired electron of one atom very strongly interacts with the unpaired electron of the neighboring atom so as to align themselves in a common direction, right? So these small volumes of uniform magnetization are known as domains. So I'll explain this to it. Suppose this is a ferromagnetic specimen, right? And in the absence of external field, suppose H is absent, or H is the magnetic intensity, or external magnetic field is absent. So I have drawn these four domains. This is just a pictorial representation so as to enable you to understand the concept in a better way, right? So this is one of the domains. Here, the atomic dipoles will be aligned in a common direction. Say like this. These are the atomic dipoles. They are aligned in a common direction. Why they are aligned in a common direction? As I have told you, because the unpaired electron of one atom strongly interacts with the unpaired electron of the neighboring atom, so that the atomic dipoles tends to align themselves in a common direction, right? In small volumes of this specimen. These small volumes of uniform magnetization. Why it is known as uniform magnetization? Because this domain, this small volume will possess some net magnetic moment, because the atomic dipoles, these atomic dipoles are oriented in a particular direction. So these small volumes of uniform magnetization are known as domains. Each domain possesses some net magnetic moment, right? So this domain, this is first domain, this is second, this is third, and this is fourth domain. So this domain will definitely possess magnetic moment along this direction. This is the magnetic moment. Clear, students? This is another domain. Here also the atomic dipoles will be oriented in a common direction, but it will be different from the orientation of the atomic dipoles in the previous domain, right? So here the atomic dipoles no doubt will align themselves in a common direction, but the alignment can be entirely different from that of the earlier domain. So diagrammatically it can be shown like this. So this is another domain where it contains atomic dipoles having orientation in a common direction. So this domain will also possess magnetic moment, say along this direction. This is the magnetic moment. Similarly, there is another domain. So domains are basically the small volumes of a ferromagnetic specimen of uniform magnetization. So each domain will have some sort of magnetic moment, which will obviously be greater than that of the individual magnetic moment of atomic dipole. So these are the domains having some net magnetic moment, which is then indicated by these arrows. Let us consider this another domain. Here also the atomic dipoles are oriented in a common direction. But here again, as you can see, its direction or its alignment is entirely different from the alignment of the atomic dipoles in the other domains. So here, this domain will have a magnetic moment along this direction. Along this direction. So students, diagrammatically I have tried to represent this ferromagnetic specimen and I have divided into 4 domains. Each domain possesses some net magnetic moment and each domain has uniform magnetization. That is, in each domain there are various atomic dipoles, all oriented in a common direction. But as a whole, the magnetic moment of these domains are randomly oriented. I repeat, the magnetic moments of the domains are randomly oriented. So the net magnetic moment of a ferromagnetic material in the absence of an external magnetic intensity or external magnetic field will be 0. In this respect, student, all the magnetic materials are same. Whether it is a diamagnetic material, it is a paramagnetic material, or it is a ferromagnetic material. In the absence of external magnetic intensity or external magnetic field, the net magnetic moment of any magnetic material is always 0. It is only when the magnetic materials are placed under the influence of some external field that it gets magnetized. Right? So, I hope you have understood this concept. So, domain are very, very small in size. Volume of domain is approximately 10 raised to the power minus 18 meter cube. And students, each domain contains about 10 raised to the power 11 atomic dipoles. Right? And as I've stated, every domain, each domain has got some net magnetic moment. So how do you define domain then? Domains may be defined as the small volumes of the order of 10 raised to minus 18 meter cube in a ferromagnetic specimen which contains atomic dipoles, about 10 raised to 11 atomic dipoles, all oriented in a common direction. So these are the small volumes of uniform magnetization. So these are the 4 domains I have drawn. Each domain has a volume of the order of 10 raised to minus 18 meter cube and contains about 10 raised to power 11 atomic dipoles. So every domain has got some magnetic moment, but if you talk about the ferromagnetic specimen as a whole, the net magnetic moment would be 0, because in the absence of any external magnetic intensity or external magnetic field, these magnetic moments of the domains are randomly oriented. So these magnetic moments can be used to represent the sides of a polygon all taken in the same order. So the vector sum would be 0. So that is why the net magnetic moment of a ferromagnetic specimen in the absence of an external field is always 0. Right? Now what we do is, let's place this ferromagnetic specimen under the influence of external field whose strength is gradually increased. Right? Suppose this is the field I am talking about. It's gradually increased. Like this. Let's complete the diagram. This is case 1. This is the second case. this is the third one, and this is the fourth one. Now can you imagine what will happen? And students, I must tell you, it's just a pictorial representation, just to convince you the concepts basically, right? So can you state what will happen? Under the influence of external field, the dipoles obviously will experience torque, and the dipoles will tend to orient themselves along the direction of the external field. But here in ferromagnetic, what happens is, due to the strong interaction between the atomic dipoles, instead of talking about the individual atomic dipoles, we talk about domains, right? We talk about domains which contain about 10 raised to the power 11 atomic dipoles. So here what happens is, under the influence of this external field, the size of the domain in which the atomic dipoles are oriented parallel to the external field, the size of that domain tends to increase at the expense of the other domains. Let me show it diagrammatically. So it should be somewhat like this. So this is the domain where the atomic dipoles are aligned parallel to the external field, isn't it? So the size of this domain will increase. So if the size of this domain increases, then the size of the other domains will naturally decrease. Which will decrease the most? That domain where the atomic dipoles are oriented exactly opposite to that of the applied field. The size of that domain will decrease the most, logically, right? So the diagram would be somewhat like this. Students, as I have told you, it's just a diagrammatic representation, just to give you a pictorial view of what will happen in case it is placed under the influence of external magnetic field. It will be like this. So basically, more and more atomic dipoles inside the ferromagnetic material will tend to align themselves along the direction of the external field. So obviously, this domain will dominate. So now it will develop some magnetic moment or some intensity. Obviously, it will start getting magnetized slowly and steadily, right? Now, if further the strength of the external field is increased, then what will happen? Again, this domain, the size of this domain where the atomic dipoles are oriented parallel to the external field will again keep on increasing further. So the diagram would be somewhat like this. So, what I have stated is, as the magnitude of the external magnetic intensity of the external field is increased, the size of the domain in which the atomic dipoles are oriented parallel to the external field, it will keep on increasing, as shown in the figure. While the size of the other domains, it will keep on decreasing. It will keep on decreasing. So students, eventually ultimately, what will happen then? If the strength of the external field is further increased, a stage will come when all the atomic dipoles of the ferromagnetic specimen will align themselves perfectly parallel to that of the external field. Or, in other language, you can state that the size of the domain in which the atomic dipoles are oriented parallel to the external field, it will occupy the entire volume of the ferromagnetic specimen, or its volume will become maximum. So the other domains in a way will vanish. So it will act as a huge, giant domain. So that's when it is said to have got magnetized to the maximum possible extent. So it will develop its own magnetic moment, which will be maximum. So I hope you have understood the concept, isn't it, students? Again, I repeat, students, domains are the small volumes of uniform magnetization. What happens is, due to strong interaction between the unpaired electron of one atom with the unpaired electron of the neighboring atom, these atomic dipoles tend to, in a collective way, align themselves in a common direction. So these small volumes of uniform magnetization are known as domains. So in para, we talk about individual atomic dipole. In ferro, we talk about domains containing large number of atomic dipoles of the order of 10 raised to power 11 atomic dipoles. Clear? So in the absence of external field, net magnetic moment is 0. But as the ferromagnetic specimen is under the influence of increasing external field, then what happens? It will start getting magnetized. That is, the size of the domain in which the atomic dipoles are already aligned parallel to the external field, the size of that domain increases at the expense of the other domains. So eventually and ultimately, a single giant domain will be obtained where all the atomic dipoles are aligned perfectly parallel to the external field. So basically, students, in para, when it is under the influence of external field, it gets feebly or weakly magnetized along the direction of the external field. But in ferromagnetic substance, when it is under the influence of external magnetic field, then it get strongly magnetized. In para, it gets feebly magnetized. In ferro, it will get strongly magnetized along the direction of the external field. So definitely, this end will acquire south polarity, while this end will acquire north polarity. So it will acquire large magnetization. So ferromagnetic specimen get strongly magnetized along the direction of the external magnetic field. Here one more important point I must share with you is ferromagnetic behavior is also temperature dependent. But mind it do not obey Curie's law. It do not obey Curie's law. Although ferromagnetic behavior is dependent on temperature. Right? Let me elaborate it. Basically, students, as we are aware, with the increase in the temperature, obviously it will tend to lose its magnetization. Why? Because with the increase in temperature, the atomic dipoles due to gain in thermal energy will start vibrating vigorously and its orientation or alignment will become random. It will get randomly oriented. So as a result, its intensity of magnetization or magnetic moment will start decreasing, resulting into losing in magnetization. Isn't it? So basically, a ferromagnetic substance on heating tends to lose magnetism. No doubt regarding that. But when it is heated to a very high temperature, or the temperature of the ferromagnetic substances increases gradually, it is increased gradually, then at a particular temperature, students, a ferromagnetic substance changes its behavior from ferro and it gets converted into para. At a particular temperature, I repeat, at a particular temperature, as the temperature of the ferro is increased gradually, at a particular temperature it is observed that the ferromagnetic substance starts behaving as a paramagnetic substance. That temperature is known as Curie temperature. That temperature is known as Curie temperature of that ferromagnetic material. So Curie temperature is the temperature beyond which the ferromagnetic substance starts behaving as a paramagnetic substance, right? And I was talking about the ferromagnetic behavior and its dependence on temperature. It do not obey actually Curie's law. It do not obey Curie's law. It actually obeys Curie-Weiss law. Ferromagnetic material, it obeys Curie-Weiss law. Which states that the magnetic susceptibility of a ferromagnetic material, is inversely proportional to the temperature that exceeds its Curie temperature. I repeat, students, the magnetic susceptibility of a ferromagnetic specimen is inversely proportional to the temperature that exceeds its Curie temperature. Tc is the Curie temperature. Let us assume Tc to be the Curie temperature of the ferromagnetic material, right? And T is the temperature at present, right? So the increase in the temperature or the temperature difference, temperature above the Curie temperature would be T minus Tc. So ferromagnetic specimen, it obeys Curie-Weiss law, which states that the magnetic susceptibility of a ferromagnetic material is inversely proportional to the difference in the temperature between T and Tc. Tc is the Curie temperature. So it is inversely proportional to the temperature above the Curie temperature. Clear? So this is known as Curie-Weiss law. So students, there are various examples of ferromagnetic substances like iron, nickel, cobalt, L-Nico. These all are the examples of ferromagnetic substances. There are various properties of ferromagnetic substances as well. So that we will discuss in the next lecture, where we will be discussing the basic differences between dia, para and ferromagnetic substances. So I hope you have understood this concept of ferromagnetism on the basis of domain theory. So that's it for this particular lecture. Do join me in my next lecture then. Thank you.